Our next presentation is by the always esteemed Andy Rayner, who is the Chief Technologist for Nevion, part of Sony. And he's going to be giving us a short presentation about media cloud connectivity, or how to get your good stuff into the cloud and back. So take it away, Andy.
Thanks, Wes. Thank you very much. Great to be with you again. So some of the points I want to cover in this presentation are elements about how we do connectivity in the cloud. And I'll give a plug for the work that's happening elsewhere on this shortly as we go through the presentation. But this slide outlines some of the things I want to cover as we go through it. Fundamentally, there are two key things we're talking about here. One is how we get in and out of software infrastructure. And then the other one is what we actually do in the way we hand data off both the control data and the media data as we go between cloud infrastructure. But let's forget the technology for 1 minute and jump back and actually look at what the customer is actually wanting. So my very, very, very simplified diagram of what customers want to do in production is A, they want to up the production value, and B, they want to reduce the cost. And if you want to actually extract that and enhance that a little bit more, they want flexibility. So the flexibility can actually help them increase the production value and reduce the cost. And then there is one thing that has to go with that as we think especially about software deployments, is it needs to be high availability. So it needs to be an always-on capability. So all of these things have to be true, and it needs to be high availability. So there's a go-to picture that I actually have in pretty well every presentation that I do at the moment, because I think it actually illustrates the whole live production ecosystem very well. We have an overarching management layer, which is incredibly important in terms of orchestrating this. But fundamentally, we actually have three fundamental elements. So the dark blue is acquisition. So this is the cameras, the microphones, and then the screens and the speakers replaying. We have control surfaces, which may be, and when I say at home, I mean domestic home. That was something that really came into its own in COVID. And then control surfaces, in the central facility or in the regional facility or at the event location. And then we've got the processing and storage, potentially either some of that on-site, but a lot of it in either public or private cloud as we move forward. So that's kind of the overall architecture, and what I want to do is just dwell in on that in a little bit. But again, couple of other benefits before we talk there. One of the things that was a bit of a challenge for people to understand when we started doing IP facilities about maybe 7 years ago was what benefit it costs, what benefit it gives, because it costs. It wasn't even cost neutral if you just look at the actual cost of replacing SDI infrastructure with IP infrastructure. But that's because we weren't yet at a point where we could realize the synergies of the efficiencies of sharing resources like people, like real estate and equipment and processing. And once you can do those things, then it costs in. So you don't just have your resolution agnostic transport. You've actually got all of these real sharing things. But moving forwards from where we are in our largely still appliance-based production environment, this is my other go-to slide at the moment, and very much what it's trying to show is where I think we're going to end up as an industry with what we're doing. So acquisition is always a real-time process. So the cameras, the microphones at the front end are always a real-time process. The consumption, whether that's being done on a lean-back device on a telly or on an iPad or a mobile, that consumption is a real-time process. And then there are the people involved in the production, the people in the gallery, the people in the sound booth. They need to actually experience the media in real time. But actually, from that moment of acquisition right through the chain to the point of consumption, it doesn't need to be a linear flow. But that's the challenge that we have within the industry at the moment, is almost everything we're doing, and I'm going to unpack that in the next few minutes, is all about trying to force that to be a linear flow. One other high-level observation is we are trying to move as an industry from the bespoke to the generic by leveraging IT and IP infrastructure and capability. And that's very much a trend which the move to software is accelerating. So not only are we moving to ubiquitous IP infrastructure, we're also now moving to software hosting. So the flexibility that IP offers has gradually changed. So when I started doing IP at the beginning of the 2000s, it was wide area connectivity that we were doing with IP, and that was starting already to leverage the ubiquity of IP transport, although some of it was not really mature enough at that point to do what we needed for real-time media services. It inherently gave us some easy ways of doing resilience. Flexibility of routing was really, really important. So disaster recovery type service continuity stuff was very, very easy to do. We then moved, 7 years ago to doing IP facility infrastructure. So this is where we're actually doing all of the stuff that is now taken for granted, if you like. We still have that resilience with the 2022-7. We're agnostic to the spatial and temporal and bit depth and color gamut, etc. We can have any number of audio channels, we can have unlimited metadata, and we can do things much easier like flexing galleries and studios and honing them onto different things. Then we get to the complete IP end-to-end, which is where I was talking about those resource sharings from the last slide. This is when we can actually start to do distributed production, so the capabilities, the processing can be in a different location to where we are, where the people are, and that can be in a different location to where acquisition is. So there's a lot of flexibility there on what happens there. And then at the very end there, which is my end picture, is suddenly we can actually have a very dynamic scaling, because if we're actually using specifically public cloud infrastructure, then we can actually adopt very different models of cost. And also, very important, the bottom one there, we're actually starting to then see the real genuine possibility of true convergence of the traditional NLE process and live. And I've just got a little slide to show that. So this bottom line here is our traditional live production workflow. All of these elements have the same point of acquisition. This middle one is what I call like the in-program highlights. So the near live NLE that the editors do within a program, produce stuff that needs to happen for replay, and then you've got your typical craft production programming. But as we move to a complete compute chain here, the difference between these really becomes the fact that this is a latency optimized version of what we're trying to do here, and we can suddenly start to use some of the compute technologies that are maturing well in NLE environments. Just another observation on where the industry is heading in terms of the adoption of software processes is it's really moving back down this chain. So if you think of this as the workflow, emission, most broadcasters are having a significant proportion of their emission done on OTT transport now. Playout is largely cloud-centric. Most playout infrastructure is now already software-based. We're just at the moment starting to see high-tier broadcasters look at using cloud-based production or cloud-based systems for MCR functions. And then that live production piece, we're moving into that now. We're doing this. We're already starting to do it for some low-tier stuff, but that's the next point of it. So we're rolling back down this line as we do that. Let's just go back and deep dive into the technical stuff for a minute, or not too deep, to talk about the inheritance that we have and why the software connectivity needs to be different. Again, I've shown a variation of this slide previously. This is the very first raster scan that ever happened. Her name was Betty Bolton. You'll see it's a vertical scan rather than a horizontal scan that we're used to now. And it was done with a flying dot scanner. So it was a single photo cell. She was in a dark room, and the light was scanned on her rather than a scan there. And our raster scan was born. And that is 90 years ago now, but we're still living in the way we actually handle transport of video, largely driven by the raster that was created back in those days. So we've obviously got rid of the CRTs now pretty well everywhere, and we've obviously changed it to a horizontal scan. But even ST2110 which I was lovingly part of formulating, still is raster scan based, and some of the elements put specific provision in to allow for raster scan and the traditional flyback times for the scanning tube. They're still inherent, unfortunately, in ST2110. And because of that, we've got this mentality where we actually linearly flow the data. And everything we do in 2110 is all about making sure it works exactly like it has done for the last 90 years. And we have a whole suite of standards, which again, I'm not trying to decry because I've put a lot of energy into actually making these work and bringing them to life. But they all define and propagate that kind of raster heritage of linear flow of data. So what does that mean with respect to what we're looking at now on compute? Well, there are two things here. I've got my red vertical, which is inherently going to be a real-time process because the flows, or I say inherently, we could challenge on that as well. But traditionally, the flows are coming in a real-time nature towards our compute infrastructure. This bit in here is the interesting bit because once we reach compute, the way we actually handle data can be done differently, and indeed needs to be done differently, because the one thing that compute is not optimized for is linear propagation of data like we are forcing it to be in ST2110. So just to talk about the way we've currently typically doing handing off of virtualized software processing functions in a production workflow. What we're typically doing today is we've got a software, a virtualized processing function here. We're typically coming in, these red lines, linear ST2110, going into a compute function as 2110. We're exercising that, we're manipulating, doing whatever process is needed, and then we're putting a lot of energy into spreading that data out pristinely to 2110-21 to make a nice linear UDP RTP flow that can go through our fabric without a problem and come back into our next function when we're doing the same thing. We're breaking it down, we're doing it like a bursty compute native function on it, and then we're conforming it to our linear world to come back out again. That's the way a lot of the way we're handing on between software functions in the way we do at the moment. Whereas what we actually want to do is this. We've got a linear source coming in, but the way we actually hand data off once we get into a concatenation of software processing functions that we are using, that doesn't need to be, and in fact it shouldn't be 2110 like, because it's actually compute doesn't work in a linear manner. There are some things we have to do. We have to preserve time. We have to know everything about the timing relationship between the elements of media data that we're processing, but they don't need to be handled in real time. That's an important premise. Again, of course, for a long time to come, we're probably going to have a hybrid environment where we've got some virtual processing functions, but we've got some appliances, what I call physical processing functions, so some boxes that are doing something. And these red lines illustrate those probably need to be linearly served with our raster heritage 2110 environment. So what's changed, or what do we need to do in a media world? We actually need a standard interface in compute that will allow us to actually hand off data from one device to another or from one process to another in a deterministic way. And there are two things that are important in that process. One is that the data is transferred with guaranteed integrity, and the other is that it's in a guaranteed time-bound manner. Those are the two things we want to do. It needs to be integral and it needs to be time-bound. Now, the challenge with integrity that we've got is the reason we developed ST2110-21 timing models is because if you have a number of UDP RTP flows, which are non-handshake best efforts send and forget technologies, if you don't have them as nice linear flows, so 1.5 gigabits is a flow at 1.5 gigabits, if you actually burst a whole load of them together, then you've got a significant risk of overflowing buffers in switch fabric and causing data loss, and then you actually don't have your signals. So what we need is a deterministic data transport technology. And the key thing about this purple bit at the bottom is that we don't really care what that is from the perspective of the media layer. We need it to be time bound and we need it to be integral, but that's all that's important. So we have a standard API there. So in some of the GCCG work, we're looking at this top layer here. Just to say, AWS has already done effectively the whole of this in what they've published as CDI. Now, arguably, that's not necessarily completely holistic in terms of what the industry needs, and there are some gaps there, and some of the work we're doing in GCCG is gap analysis there. But they have actually overcome, or they've addressed both of these issues. In some ways, it would have been nicer if they'd just handled the purple bit and let the industry do this wrapper. But that's, we can live with this because they've published this on GitHub as an open source. So you can go to GitHub and you can download all of the information about CDI. And the intention is that we're going to maybe make some modifications as an industry to that, and hopefully they'll adopt that back. But it's important, there are other cloud providers and there are private software platforms you want to run. So SRD, whilst that's the technology AWS are using, we're not beholden to that. What we need is those two things. We need guaranteed a time-bound nature, and we need guaranteed integrity. Those are the two things that we have to have. We actually were involved in the very first trialing of this, which is unbelievably is almost 2 years ago. We did some testing with some ground and software instances to actually push and go via CDI in the cloud, and that's almost 2 years ago. And since then, we've actually been working, providing and testing, interfacing in and out of cloud infrastructure using the CDI in the cloud as is. And it's worth saying, you can check this out on Amazon's website. This is public domain information, but there's some good descriptions about what SRD does to provide that time-bound and deterministic nature. Now, some other work that we've been doing in VSF that's applicable here as well is the ST2110/WAN, because as we move to distributed production, we break outside of a campus. We suddenly need to transport media flows and, importantly and more complex, the control flows associated with those over wide area connectivity. And that belies some challenges with security and isolation when you're actually trying to do this, bearing in mind the entities you're handing between could be competitors, but certainly could be going into DMZ land where you don't know what the risks are. And the handoff of data we're talking about could be between cloud and compute infrastructure equally as well as an OB truck or a physical facility. And we did some work there with on the control plane using a constrained version of NMOS, and you can find out more about this in other presentations online that actually describe the way we're actually doing that work. So that's all available. Some of you may have seen some excellent work that the DPP did last year that I was proud to be a little bit involved in the discussions on, which actually defined some of the different scenarios of the way remote production is going to be done moving forwards, or is being done. We actually added a couple of models ourselves. If you remember back to that very early slide, we have acquisition, we have processing and storage, and we have control. Those are the three key elements. And what these lines are really showing is which elements are co-located. And very specifically here, this one at the bottom here is typically the one we're referring to here, where you've got an acquisition location, you've got your cloud processing and storage, and then you've got a control location, which of course could be the same place as that, but may well not be. Just a reminder, coming back to this model I showed at the beginning, the important thing is that we have time alignment between elements at these points, and the timing of the information that's being processed through here needs to be such that we can track time. So tracking time through the elements is very important. I actually made comment in my previous presentation to this on this slide is in terms of time alignment. When we're starting to look at aligning time, there are some questions as to what is important to do here. We have like typical lip sync requirement of being within a few milliseconds. If we need coherent audio, if we need a lot full alignment between phase coherent audio, then we've got to be better than 20 microseconds of alignment. And then arguably, if you're just talking about absolute time presentation of a program, as long as you're within a frame, and sorry, I'm using European frame rates there, then that's where we go. But one of the other things that's important once we get into the cloud is how we actually handle absolute time and what time matters. There was some, as we moved into compute originally, there was some concern that we wouldn't be able to propagate PTB within cloud infrastructure, but my challenge is we don't need to. We only need very accurate timing at the end of a chain when we're actually reconstructing back to linear world. So actually the only timing that we need to have within a compute infrastructure is the typically millisecond accuracy that we can achieve by NTP. That's well good enough for what we need to do, because we're rippling time, we're actually creating an end launch time, but the actual minute, we're not trying to do that minute timing that we've been doing with 2110 throughout the compute chain. And we've got different elements of time that we're worried about, that we can think about here. We've got absolute time, we've got relative time, which is really important, and then we've got production time that can be something different. And there's also some challenges as we think about time when we've actually got synthetic sources that are coming in. What is the intended creative time of the synthetic source? Also, if we're actually capturing content previously and then doing a replay, maybe a multi-ISO replay, what's the intended production value time of that as it comes in? So there's some challenges in what we're handling here. Just rewinding to what 2110 gives us in terms of time, because typically if we're thinking about cloud infrastructure, it's quite likely that those cameras that may be sourcing that, assuming they're maybe not native 5G connected, but if they're more traditional system cameras, then they will be capturing time with and time stamping the RTP with a ground-based PTP timing reference. And whilst that timing reference is not going to be needing to be handled in the same way through cloud infrastructure, that timing information needs to be maintained. So whether we're doing integer frames of video in the cloud infrastructure, or whether we're doing partial stripes of video frames, for instance, and appropriate clumps of audio, the timing information that from the origination, from the capture of the video and audio, is important that's rippled through the process. So when we have our system that can actually compute time, that can be aware of that. It's worth obviously also observing that we kind of have a quantization of time in the way we actually think about time for media as we're carrying it. We have in the 2110-20 world, we've kind of really hijacked RTP a little bit to how it was intended, because we actually freeze the timestamp in RTP for all the samples relating to the moment in time that is that video frame, whereas in audio, it actually ticks at the sample rate. That's a more classic use of the RTP timestamp. So getting back to this this processing time that we have if we've got software elements in the chain. The challenge with the software element is it can deliver things within a certain time, but that time is non-deterministic. So I've put this very, very simple curve. It probably doesn't look anything like this, but what we're interested in when we're actually interconnecting these virtual elements within software and a software infrastructure is we're interested in this point here, which is the worst case time that a process is going to take, because the budgeting of time of our concatenated, if you remember those concatenation of functions, our concatenation has to assume or allow for the worst case propagation or execution time when we come to do this alignment here. So we need to have some orchestration that actually does the maths on this. And this aligns a little bit to the work I was talking back an hour ago that we're trying to do in SMPTE 21.10.11, where we're trying to actually accommodate this software world, this new software world with software connected environments, as well as the traditional appliance-based world. Then we have all of the things that we actually want to do within cloud infrastructure in terms of the way we control them. So we actually The great thing about virtual infrastructure, as I said, in terms of the benefit is it's transient. We can make it only present when we're actually needing it. So we have a whole host of work we need to do at the control plane to instantiate and tear down those resources. We need to actually manage our resources. So manage the amount of resource we're actually using on aggregate and the booking of that, etc. We need to do the time domain management, which I've been expanding on. We need to manage flow control and connectivity control. So this area here is something that we're starting to work on, using again some elements of NMOS within cloud infrastructure to allow us to do that connectivity. But flow control at the moment is kind of cloud vendor specific in terms of the way we actually do that. Okay, I've rattled through a whole load of bits here, but hopefully it's teased your thinking very specifically on this intra-cloud connectivity. If you're interested in learning a bit more or even partaking, the VSF have got some active work in the GCCG, and SMPTE have got some work in the timing aspects of it that we're doing within 2110-11. So I know both of those groups will be very excited to have further input, and not necessarily a commitment of input from you to actually join and slog through the standards work, but user stories are really important. So if you can actually think of scenarios or gotchas that you maybe are experiencing or have experienced or might experience in your workflows, then do share them, because we'd love to actually include those. Thank you very much. It only remains for me to say I'd love to buy you a cup of tea. If you're ever in the UK, give me a shout out. Thank you very much for your time, and back to Wes.
Thank you, Andy. Does anybody have any questions?
Sorry, I couldn't resist. Cloud, that it seems to me that it's really software to software. So will that be addressed in that working group, that it's not really needing to be cloud located?
Absolutely, yeah. So it's intra software, yeah.